Hello everyone. Thank you all for coming to the first installment of the pre-HackNC workshop for HackNC 2019. This workshop is hosted by the Society of Industrial and Applied Mathematics on campus, which is an organization of people with a special interest in industrial and applied mathematics. We have a talk today on exploratory data analysis given by Wesley Hamilton, the president of SIAM, the UNC chapter for Society of Science and Applied Math. The workshop will have some code and some data that's available in that link under workshop resources. And if any of you is interested in joining the UNC chapter for the Society of Industrial and Applied Mathematics, feel free to sign up with the second link on the whiteboards below. Thank you all for coming. Without further ado, Wesley.
Is that good? Can you hear me? Well,
Can we hear him?
no. Well, I mean, it's more for the recording.
Yeah.
I'll speak quiet. Can everyone hear me? All right. Okay. Cool. Thanks for having me. So, as I-Ching said, my name is Wesley Hamilton. You may or may not know me. I'm a grad student in math. And what I'm going to talk about today are a few exploratory data analysis techniques, right? And so what is exploratory data analysis? Well, it's exploring your data before you do some serious, like polishing and, putting everything together to present it. Right, okay, so what are we going to do today? Well, a few kind of background, general idea things. The three main families of techniques that I'll introduce and I'll give a few examples for are PCA/MDS. PCA is principal component analysis. MDS is multidimensional scaling. These are very kind of linear techniques. The next family, really just one, is ISOMap. But ISOMAP's a family of these kind of nonlinear manifold learning techniques. Some other ones are local linear embedding, local tangent space alignment, etc. But here I'm just going to talk about ISOMAP, in part because it's the simplest. Finally, this last family of things, of these techniques, are these kind of spectral techniques based on, or essentially graph-based methods. And so the progression is, here we have a lot of structure, a lot of rigidity. We want a linear space. For these manifold techniques, we still want a surface, but we don't care if it's not a linear space. And then finally, with these graph techniques, we're not making any assumption about the underlying surface or space. But yeah, so kind of in the spirit of this talk, right, the topic being exploratory data analysis, a lot of kind of the pictures, the results are going to be very rough, right? I'm not presenting to you, final analyses. I'm not, making predictions. I'm not saying this is what you should do, this is what we predicted, etc. These are just techniques to start to get to know your data to inform further analysis. Right, so why explore? Well, right, we have a lot of intuition for, intuition, looking at 2 or 3 dimensional, plots, clusters, whatever. We can make sense of those very easily. Okay? Usually when we get data, it's very high dimensional, so we don't necessarily have, right, a nice way to plot it in 2 or 3 dimensions. And so a lot of these techniques are dimensionality reduction. They give you ways to plot your data set in 2 and 3 dimensions. That lets us visualize the data. It also lets us maybe visualize important subsets of data. Another really nice thing is it's unsupervised. So I say semi because once you start plotting, once you start visualizing, then you can use that to inform maybe how you slice the data and do some other, or maybe take subsets, whatever. But for the most part, it is unsupervised, so you don't have to be very smart about the approach. And why not? And so in particular here, we're really going to be focusing on, say, the intrinsic topology and geometry of the data. Topology just means connectivity, what points are close, what points are far. Geometry, you add some more rigid conditions. You also want structure, you want scales to be preserved, etc. And so for today, so unfortunately I wasn't able to prepare any text-based data, not using anything like, was it term frequency, inverse density, or inverse document frequency. There are a lot of text-based techniques out there, but here we won't be using any of them. Instead, so I have two data sets that I cooked up, two data sets that I got from sklearn, or scikit-learn. As you can read, one of them is a collection of 1,000 points on a two-dimensional sphere embedded in a 100-dimensional space. The next data set is a family of these pinched circles, and I have a picture to make that clear. This third family is called the MNIST digit data set. It's a collection of handwritten digits. And then finally, there's this California housing data. That's based on, I think it's the 1990 census. And yeah, so in the code, which I made available, towards the beginning, you could see where I construct these data sets and where I call things in. There is a command to read in this California housing data directly through Python, but when I tried doing that, I kept getting some error with making the call to the website, so I downloaded it manually and I also included that. So what are these data sets? Well, 1,000 points on a sphere, I just, called the sphere data, looked at the values, this is what we get, right? So in particular, it should be a 1,000 by 100 array, right? And it's fairly dense. Most of these entries are, all of these entries are non-zero, okay? So even just looking at it right now, there's no clear pattern. The next data set is this family of pinched circles. So one thing to note is the scales might throw you a little off. Mainly just this bottom row. If you look at my code and figure out how to fix that, then, I don't know, great job. But anyways, this is the data set. What's happening is, first we have a family of these circles that gradually become pinched in the center. And then what happens is we take kind of an all the way pinched circle and rotate it, and then we unpinch. Okay? So that's the second data set, this toy data set that we'll be looking at. Here are a few of the MNIST digits. They look really rough, but that's, I don't know, how they were vectorized, how they were scanned, whatever. I think if you change the color scheme, they look a little better, but these are the data files that were analyzed. And then there's this California housing data as well. And so all four of these data sets, again, you can access through, or construct or get through the code. Let's see. So, with this California data, the first thing we see is that we have longitude and latitude. Okay? The thing is, all of these samples, are coming from California. So all the longitude and latitude coordinates, they're going to be roughly near each other. Okay? So what we can do is just go ahead and plot them. Right? Technically, if we try to plot them in this linear fashion, there's going to be some discrepancy, right? The Earth is curved, right? A square is not. is it Gauss-Bonnet or Gauss's theorem egregium? There's some theorem that tells you that you don't have, say, an isometric immersion that, I don't know, curvature gets in the way. Point I want to make though is that since we're only looking at California and not say like the whole United States or locations all around the world, for our purposes, it's fine to just plot them in a square. Okay? And it really does look like California. So I have a map of California. Right, so looks like here, San Francisco-ish, Sacramento-ish, LA-ish, I think Fresno. I don't know California cities. I just got them from this map. Okay, so what else can we do? One issue with just plotting, right, the longitude and latitude like this is we may get overplotting, right, in the sense that, right, these regions over here, they're all just dark. Okay, so we don't have a sense of how many data points are contributing to that kind of darkness and filling in that area. So one relatively quick thing we can do is take this kernel density estimate. And so what these kernel density estimates do is they construct the probability density function that approximates kind of how these points might have been sampled. And so then what we do is we take that probability density function and just plot, say, height values or some other values there. And so again, something to note, the axes are a little misaligned. This goes to 126, that only goes to 124. But we still get a rough idea of, right, down near LA, there are a lot more X's that are plotted versus up near San Francisco, right? And that we can read off because this kernel density estimate says kind of this probability density function is a lot higher right here than it is up there. And so that's another quick thing we can do to get a better sense of, right, what's happening with this plot. It's not too bad to do in Python, but it does take a little bit. The main command is this Gaussian KD, this kernel density estimate. But to get the data in the correct way to actually use that, you have to do some pre-processing. In particular, right, so these Cali map bounds, you say, you know, what box you want, and then reformat the things, get the values. So these values are the actual housing coordinates, and then we construct this kernel based off of the actual housing coordinates, the city coordinates. And then we sample this kernel density estimator on this grid that we constructed. And so that's what's happening. What you could do is then sample this kernel density estimate on the actual housing coordinates, but anyways. And this, so yeah, again, this is available. Feel free to play around with this, etc. Feel free to make better visualizations than I have there. But again, this is all very crude stuff, right? Getting a quick idea, rough sense of what's happening in this data. What else? So then, right, another thing we can do is start going through and looking at some of these other values, right? So looking at the data, right, longitude and latitude, sure. We also have housing median age, total number of rooms, total number of bedrooms, population, households, median income, median house value, and ocean proximity. Something to note right away is that kind of the scale of these median income values are not on the same scale as these median house values. Okay. So that's something then that kind of we would need to take into account if we want to start learning or start making the model, etc. Okay. Something else that came up was, I think it's total bedrooms in this data set, it has a few NAs, and so that messed with some of my coloring procedures. And so I don't think I included them because it was too messy. But that's another thing, another quick, if you, right, take this total bedroom columns, look for the minimum, it'll show NA, but the others didn't. And so because of that, I chose not to do any further analysis. But back to this, right, so on the right is a plot of the sorted housing median ages, just to get a sense of the distribution. You could also do a histogram. On the right, or on the left, it's the same map with each of these X's colored according to the housing median age. Yeah, so conclude what you want about where older people like to live and younger people like to live. What else can we do? We can take median income. So something to note on the right is that it's not as linear as, say, this housing median age, right? There is that sort of S, or rotated S shape, whatever. So to color this map, instead of just taking kind of these values as they were, right, what's going to happen is these data points closer to the max, they're going to get colors closer to, say, 1 before transforming to this color map. Okay? And then there's a relatively large gap before most of them. But right, most of these data points sit in the same sort of range. So all of these cities are going to get roughly the same color. Right? If I hadn't log transformed, most of this would be closer to blue, and there would only be a few really sharp reds. Okay? So because of that, I chose to log transform that data and then do the same thing as before. Okay? Feel free to try coloring this map without log transforming it. See what the difference is. Yeah. So even after log transforming this, okay, so this is essentially what I was saying might happen back here without transforming it. We get a lot of reds, not very many blues. Part of that could be, well, the data itself is already closer to being linear than like an S-shaped sort of thing. So maybe I didn't need to transform. The colors here were transformed, log transformed. So, right, in the code, see what happens if you don't transform it. See if it looks better. Something else we got with this data set was a column that told us where each city was in relation to the ocean. And so to get this list, one cheap method is to take the whole column, cast it to a set, and then cast it back to a list. Python will just isolate the unique entries. I don't know if that's the quickest way. Another thing you can do is just loop through everything and take out unique things, but that's the way I like to do, and it works fairly well. But what we can also do is just plot cities based on, or kind of use these labels as our color scheme, and then kind of plot cities, see where they are based on this. And so the picture won't be very surprising at all, right? I don't have the conversion right away, but my guess is that blue are, where are the labels? So you have near ocean, less than an hour from the ocean, inland, near bay, and island. So looking at this, green is probably island. We're getting some overplotting, but it looks like there's orange up in here. So San Francisco is near the bay. So orange is probably near bay. Blue is probably on the coast, or less than an hour. Red is inland, etc. Right. So one thing we might ask then is, how does median household income, median age, how do these values correspond to the labels as they're colored here, right? That might be a natural first question. So then that would be, something you could look into further. But yeah. So these are all some very rudimentary, right, analyses that you can do really without much analysis, right? The most kind of complex things were that kernel density estimate and log transforming, but for the colors. Okay, otherwise it was all fairly straightforward, just quick representations. So for a lot of these other techniques, we'll be comparing, say, feature vectors, vectors that collect, I don't know, just whatever data, whatever numerical, quantitative data we're looking at. And so, right, to do that, we need to have a notion of distance or a metric on the data. So a few popular ones, right, if you have vectors in Rn, you can just take, say, like the L2 or Euclidean distance. Depending on the data, you may have issues with scales involved, right? So for this California data set, one of the columns was age, another column was median household value, right? One was in tens, one was in the hundreds of thousands. Okay? So if you're going to do something like an L2 or Euclidean norm on that, then I guess be a little smarter about it, right? Transform your data in some way so that the scales are comparable. Okay? Other popular options, L1, where you just take, or the Manhattan distance, where you take the absolute value of the difference component-wise and then sum them up. L infinity, you take the maximum of all distances or between coordinates, I believe. If you have extra structure, right, well then you can get different sorts of metrics. So if you're on a surface, say like a sphere, one natural distance function is geodesic distance, right? How far do you need to walk along the surface to get from one point to another? If you have a text-based data set, you can use, as I mentioned before, this term frequency, inverse document frequency, where you take your collection of documents, right, run through, pick up all unique words that show up in any document, and then run through again, and for each document, for each word in that document, count how many times it appears, but then normalize for how long the document is. That's a decent vectorization that you can then use to cluster, analyze, do whatever to your data. One that'll come up later, and I'll describe in more detail later, is this Preprocessing distance. And it gives a very nice way of measuring distance between shapes or curves based on landmarks. So for that, for the pinch circle data set, right, the landmarks would be points along the circle. Okay? And so, okay, I'll talk more about that later. Another one, if you have time series or some sort of functional data, something you can do is just take like a function inner product, something like I guess a functional L2 norm. But all right, otherwise, be creative, right? Depending on the data you're looking at, depending on what questions you're trying to answer, feel free to come up with your own notion of distance. For this California data set, maybe you want to upweight age and downweight household value. That might be one notion of distance for that kind of data. But, yeah. So, why use metrics? Well, we want to go from a collection of data points, these x of i's, and we want to output some distance matrix. Okay? So a lot of the techniques that Python has built in, their vectors, they'll assume that the vectors are already, or your data points are already in Rn. And if you want to instead work with your distance matrix, there's a little extra work that kind of gets involved. But one nice thing about working with the distance matrix, instead of vectorizing your points and putting them in Rn, is you have a lot more freedom for what metric you're using. You don't have to transform, vectorize, and then use the built-in Euclidean unit. So the Preprocessing distance is a very nice example of that. And in the end, we want to find a lower dimensional space, representation, visualization for these points. Are there any questions so far before we get into the techniques? Cool. So the first technique is this thing, it's in the linear setting. Our assumption is that our data sits near a hyperplane. And our goal is to figure out what this hyperplane is and where the projections of our data points should be. Okay? And so I have a very, very rough sketch. So these x's, these are our data points. They're sitting in some high-dimensional, three-dimensional space. 3 is high-dimensional. And we want to look for a two-dimensional hyperplane such that when we project each of our data points onto this hyperplane, we're minimizing these distances, the sum of all of these distances. Right, so in a sense, figuring out what these projections are and figuring out what this plane pi are, they're equivalent. Those are both our end goal. Yeah, so I'm not going to get into the actual, how is this computed. One easy way that you can, code up yourself is by using the singular value decomposition of kind of this covariance matrix thing. But Python already has a built-in PCA sort of solver. Right, so in short, use linear algebra. Okay. So here's a sample of the code that's used to compute some of the next few pictures. So what we're doing is we're kind of defining this, this PCA 2D is equal to capital PCA, etc. We're defining this, say, model, the solver, right? And for a lot of these other things, that's the very first step. Then what we do is we feed a data set of interest to this solver. Okay? And then out pops coordinates for our embedding. Okay? And then this line is just plotting everything. Scatter is a wonderful thing, wonderful command. And then depending on if you're using, I think Spider, whenever you call plot, it'll display the plot automatically. But if you're using something like IPython or maybe the terminal, you also have to explicitly say show the plot. Okay? So this stuff would depend on what IDE, if any, you're using, but that's the gist of how to use PCA. So what happens? Well, here's our sphere data, right? So looking at these numbers, there's not necessarily any clear pattern, and I don't know which dimensions our two-dimensional sphere was embedded into, because in the code it's set up to embed into 3 random dimensions. I guess unless you fix the seed, but I didn't. So here's what we get if we embed into 2 dimensions. Okay. So what PCA is doing is taking all of these 1,000 100 dimensional vectors, doing some linear algebra, and deciding that, okay, this axis and this axis are the most important. Okay? And so those two axes we're going to project every point of the sphere onto, and then that's the picture. Okay? Something to note though is that, right, I keep saying sphere, right? Spheres are hollow, but we're getting plotting, right? Some of these points are plotted in the interior. Okay? So one of the assumptions that went into get this picture is that, right, our data sits near a two-dimensional plane, okay? Which is a valid assumption, and especially if we're doing a quick analysis, then that's fine. But what we can do is then, okay, go into 3 dimensions and see what happens. Okay, so in 3 dimensions we get the whole sphere again. Right, if you run this yourselves, at least in IPython, you can actually move it around. But those lighter X's, those are in the back. Darker X's are in the front. Something else is I added a bunch of noise to the sphere, so everything's not exactly on the sphere, right? But most data is somewhat noisy, right? We're happy that we can see the sphere, okay? From these 100 or 1,000 by 100 samples, we found our sphere. And again, I can't tell you which 3 dimensions this was hidden in because I don't know myself. Something I might point out is, right, going between these 2 pictures, this picture right here would be what we get if we took any plane through the origin and then projected everything onto it. Right? So with this extra dimension, we have that space to more accurately plot everything. So any questions on kind of this or the picture that we're seeing? Okay. So MDS is it's related to PCA. Maybe one quick description is that, so with PCA we're working with the embedded coordinates and we're looking for a hyperplane in those embedded coordinates. For MDS, we don't necessarily have those embedded coordinates, but we have a distance matrix corresponding to the points. Okay? And so the end goal is still the same. We want to find a plane to project everything onto, but we don't necessarily have these Euclidean coordinates kind of to base that off of. Instead, we only have the distance matrix. And because of that, right, it's a little more involved. There's some optimization that goes in, maybe like a gradient descent. Depends on what actual method you want to use. But there's some fancier tools going on. The end goal is the same. Also, the code's very similar. All right, so again, what we're doing is we're kind of constructing this this general solver object, and then we're feeding it our data, and out pops our embedding coordinates. So down here, these are just for plotting. Since we're plotting in 3D, we have to do a little extra. The packages that I'm getting this from, and Manifold and PCS from before, those are all in the code. But yeah, so this is what we get. I promise I actually, ran a different code, and I don't just have the same picture as before. But right, so when we can use PCA, MDS and PCA will give you the same answer. It's just when we can't use PCA, MDS is still applicable. And so we can do that with this other data set, these pinch circles. So again, what's happening, right, is at the top, we start with a circle, we start pinching it until it gets all the way pinched, and then we rotate it, and then we unpinch. Okay? So each of these circles, I believe, they're either 100 or 500 points, some large number of points, those x's. Okay? And so right, one way of thinking of each of these data objects is as a vector in, so they're all in two-dimensional space, but there are 500 of these entries, or 100, maybe 100, whatever. So each of these x's, right, 2 dimensions, 100 of them. So each of these curves corresponds to a vector in R, maybe 200, right? Just take that array of coordinates, stack it, stack the columns, that's a vector, okay? So we can think of each of these curves as a vector, okay? Well, since we have a vector, we can do PCA, and here's what happens. So the color scheme is, I think, green, red, blue, I don't know, something. Looking at the data, right, it should wrap back around itself, right? We start with a circle, go through these motions, end up back with a circle, ignoring the axes, right? Our start and end point are a circle. So in a sense, our data, right, should loop back around and get back to itself. The start and end points are the same. The issue is that here, right, each of these x's corresponds to a different circle. The colors are the same as what they were before. Right? They don't loop back to themselves. So, right, that might be a little surprising. The question is, what's going on? Is it something with the data, or is it something with how we were working with the data? And so in this case, it turns out to be how we were working with the data, right? To get this PCA plot, we just treated everything like a vector, and then compared them element-wise, right? That's how we computed the distance. The issue, though, is that, so this point, say, points around here. After the rotation, points around here get mapped up here. But over here, more or less by how these were constructed, so this point corresponds roughly to this point. That's how they are in the data set, that's how they're constructed. Okay? So when we're computing these Euclidean norms, we're looking at, we're comparing the distance, the coordinates of this point to the coordinates of that point, right? And those are going to be very far from one another. And that's where we're getting this gap from, okay? So the fact that there's this gap is coming from how we're measuring distances, how we're working with the data. So a workaround is to use the notion of distance that's more intrinsic to kind of the data, that's intrinsic to shapes. So here's a very rough sketch. We have two curves, x1 and x2, okay? And we want to measure their distance. So how we go about that is, well, we rescale them. So each of these curves as vectors, they have norm 1. Once they've been rescaled, well, then we center both of them, right? So now this x2 is this dashed curve right here. And now that they're centered, what we want to do is rotate one of them so that more or less sits on top of the other, as close as we can get, and then measure that vector distance. And so that's this thing called Preprocessing distance. And then if we do that with this data set, then indeed the loop closes in on itself. And we do see that indeed this data set's this circle. So the lesson there is, right, keep in mind what kind of metric, what kind of distance you're using with your data. So what else can we do? So manifolds, right, the difference here is that we don't necessarily care if it's a linear surface that the data is sitting close to. Here's a rough sketch. we have a bunch of points in our capital N. Capital means it's big dimension. We construct a distance matrix, however we want, Euclidean, whatever else. And then from this distance matrix, we want to kind of approximate this nicer surface, right? So maybe the fact that all of these points sit on the surface, it's not clear at all from their coordinatization in Rn. And so that's the idea with manifold learning or nonlinear dimensionality reduction. One of the simplest and quickest-ish procedures there is this thing called ISOMap. If you look at the paper, their algorithm works with roughly eigenvectors of this distance matrix. Okay? But it's more or less equivalent to performing sort of MDS with nearest neighbors instead of with the whole distance matrix and the whole data set. And so here's an example of the code. So different from before, instead of just saying what dimension we want, we also have to say how many neighbors we want to use in these computations. But otherwise, the setup's the same. We define a solver object, and then we feed that solver our data. Okay? And then there's the plotting. So this extra piece right here, I'm writing labels for the digits. And you'll see why that's worthwhile. Right? So again, here's the data set, sample of the data set. Here are all the data points projected into R2 with colors corresponding to labels. Right? So the issue is, we start to see clusters, right? We start to see kind of the distribution, the shape of this data, but as it is, we don't know which clusters are which. So quick workaround, well, plot some of the labels. So ones are kind of up in here, sevens, 8s, 9s, 5s, some ones over there. But now we're getting more of a sense of how this data is spread out, kind of what manifold this data lives on. Right, so going from this representation down to here. I believe this is PCA, or one of them's the other. Yeah, so on the left should be ISOMap, on the right should be PCA. I think with PCA there were a few weird ones, but anyways, just different ways of looking at the data. Something else I want to make explicit again is I'm not trying to make any conclusions. I'm not giving any suggestions. This isn't polished work at all. The point is just to get a sense of what's happening in data and a quick visualization of things. Okay, so the last kind of procedure, family of procedures that I want to mention are these things based on just graphs. Okay, so you could argue that the other ones that we've looked at are based on graphs in some way, right? So for ISOMap, we're looking at nearest neighbors, right? What's stopping you from constructing the graph based on nearest neighbors? In some sense, that's what the algorithm does. But here, we don't want the output to have any sort of assumptions on the structure for where the data should be. We're just looking for connectivity, not scale. And again, we're looking for a lower dimensional space. So this technique that's fairly popular is called t-distributed stochastic neighbor embedding, or t-SNE for short. And actually describing the algorithm is a little more involved. There are a few more formulas, but the idea is that you want to you want to treat connections between data points as the likelihood of jumping from one data point to another. So you're transforming this data set and this distance matrix into this kind of random walk setting. And then you want to find an embedding that minimizes sort of probabilistic energy. So before, the energy that we were trying to minimize, especially with MDS, was the, I don't know, you might say, so yeah, the energy we wanted to minimize was the sum of distances from the manifold or from the hyperplane. Here, the energy we want to minimize is this Kullback-Leibler distance. I don't do a lot with this sort of probability in statistics, so I can't speak very knowledgeably about this stuff. But the technique works. And it's built into Python, kind of, sklearn. So a rough sketch is, right, now again, we still have our data in R capital N. We take our distance matrix, and then we want to find an embedding of this graph. Okay? So again, we're not making any assumptions on structure, on the geometry. We only want the topology. Here's one way to run it. Right, setup's more or less the same. You define this model, essentially this model constructor object, and then you feed it your data. Right? And so then, of course, you can play around with different parameters. Those parameters are the ones that came from the tutorial that I was following for this stuff. But otherwise, right, feed your data, get the coordinates, plot the coordinates. Right? And then, like before, I want to plot the labels as well to get a sense of where these clusters, say, were in space. So here's what pops out. Right? One thing to note is that we get much better separation between these data objects. Right? With ISOMap, there was a lot that was filled in, right? But here, they're a little better spread out, okay? Part of that is because we're not making any assumption about the scale between these objects. We only want connectivity information. And so what t-SNE is picking out is that all of these 2s are much better connected to each other than anything else. All of these 9s are much better connected, I guess, except for this cluster and this cluster, but right, the idea is there. We don't care about scale, we don't care about the surface, we only care about connectivity. And t-SNE does a pretty good job of picking that out. So then the question is, well, what if we embed in higher dimensions? Do we get even better separation, right? Because instead of trying to project everything onto this 2-dimensional space, or use 3 dimensions to pull things apart, here's a picture. From this view, it's not very clear, but this may, I mean, especially if you have kind of work with this in your own, say, an IPython or your own environment, if you move this image around, you may have a much better explanation of why we had these seemingly or these clusters of 9s that were far away from that big cluster of 9s. Well, maybe where these 9s sit just kind of fold over in some way, which was lost in this 2-dimensional representation. But in 3D, since we have more of that room, we can pick out more of the structure for this data. So those are all the techniques. What are my suggestions? Well, do the simplest things first. Just start plotting, take means, get a sense of the data. From before with that California data set, you could use histograms, or you can sort your data, plot it, get a sense of, 1, what the distribution is, and 2, kind of how fast those distributions are changing. Okay? look at means, other whatever standard statistical tools you want to do. Full disclosure, I've never actually taken a stats course, so I don't know a lot of these standard statistical tools. ANOVA, I think, is something. Anyways. But maybe after you've done them, or in addition to them, right, try using PCA. Okay? PCA is nice because it's relatively simple, but it's also quick. And so it's easy to get quick plots, quick distributions of data. MDS is also nice, but because it's a more involved optimization procedure, it can take a little while longer to actually get the solution. ISOMap's also nice. Maybe I should have switched these. t-SNE is wonderful because you only want connectivity information. And maybe a lot of the time, this manifold assumption is too much for the data, right? But again, it depends on the data. And use color. It's great for getting a quick sense of the distribution of where different values are, etc. Right. So one example. Maybe this isn't a very good one, but the ISOMap one. So if instead of only plotting, I think I took 200 of these points at random and I plotted the label up there. If instead I took every point and instead of having these dots, I plotted that label, it might be a lot harder to figure out what these different clusters are. Okay? In particular, because you're going to get a lot of overplotting, especially in here and up here, it's just going to look black, and so you won't really get to see what these labels are. Okay? Color is a great workaround. Cool. So here are a few of my references. Stack Exchange is wonderful. Color maps, there are a lot of choices I made. So the color map I chose, I didn't want to have any white in it. A few of the really nice ones have white right in the center. So depending on how it's plotted, you might have, I don't know, a bunch of colors, and then it looks like your data disappears, and then you get a bunch of colors again. Okay? So that's something that I wanted to avoid, so I didn't use some of the standard red-blue ones. But you have a lot of choices for color maps. Make use of them. Scikit has some wonderful tutorials and demonstrations about not only these the techniques that we have here, but a bunch of other techniques. So this thing, local linear embedding, is related to ISOMap. It does a little better than ISOMap in some cases. It's just another technique. There are a lot of other graph-based embeddings that are out there. A lot of them are much simpler than t-SNE, but again, it's just, there are a lot of different tools out there for kind of visualizing your data, embedding it into lower dimensions, and otherwise just getting a quick sense of what's going on, and giving you an idea of where to go from there. And I think that's everything. So thank you. Are there any questions? I can put my email up on the wall if anyone wants to contact me after this.
Oh yeah, so real quick, a lot of our members are beginners and may not necessarily have all the technical expertise to know about PCA or all these like really advanced techniques. What do you think are some steps that they could take to maybe just get a refresher before HackNC starts?
Play around with, plan at live. This might be a little light, but okay. So the biggest suggestion I have is use, so if you go to some website, So scikit-learn datasets. Scikit-learn has a lot of sample datasets. So this California housing data that I was exploring a little at the beginning, and this MNIST dataset, these are both available through this collection. And so kind of something I said before was I had issues getting the California dataset, but I found it on GitHub, downloaded it, and made it re-available. These might actually be outdated, or maybe I was just using the wrong package.
Do you have any tutorials that maybe you followed along that maybe they could follow along to?
Yeah, give me these, where was it? So these two things here. So this comparison of manifold learning techniques has running code for testing out, so like MDS is one of them, ISOMap's another, spectral embedding is something I didn't include, but that's another technique. They have t-SNE here. And more or less, right, so you saw that init PCA random state equals 0. This is exactly where I got the t-SNE line from. Here you can see outputs of each of these techniques. So this would be one place to get these techniques. I'm trying to figure out where this dataset's utility was. I think it was scikit, yeah, it was sklearn. So my main suggestion would be use the sample data sets that Python has in sklearn. Where to get them? If sklearn's, what is it? Tutorials are a little iffy. Something you can do is, so once you've imported, what is it, from sklearn, import datasets. That's, I guess, line 17 of the Python code that's included. If you type help parentheses datasets, it'll run you through the information they have about that package. And so in particular, you can see a list of the training data sets and the test data sets that they make available that you can play around with. Okay? But in getting practice, getting prepared, a lot of it's really just playing around with the data set, playing around with these tools. Right. One thing you can do is try to get some results about this California housing data set. So I had one plot here. See if you can find a correlation between what these labels are, these proximity to the ocean, and maybe median house value. Right. So in general, it looks like the closer you are to the ocean, the deeper the red is. Right. So see if you can quantify that relation. Median income looks like it would also give you a good correlation or connection between the two. Housing median age, maybe not so likely. Right, and so the nice thing here is, well, okay, looking at this plot, it doesn't look like this is going to correlate or correspond or whatever to location to the ocean as well. So in whatever model, whatever analysis we want to do, let's not use this column of the data frame. Let's only use, say, this and this. But that would be my main suggestion. Find a data set, like the housing data set, play around with it, run through my code, see what the different things are, especially the plotting. That's really crucial in a sense. Right. Having working plots here saves a lot of effort, trying to figure it out, say on Saturday. I wasn't able to figure out color bars in a quick way, so that might also be something to play around with before the hackathon. Quick ways of getting color bars on these plots. I also didn't do any contour plots. The contour plot would have been really good right here. See if you can get a contour plot going. But otherwise, play around with data. Yeah.
Great. Well, thank you so much. Can we give one final round of applause to All right, so quick things before you leave. So obviously you have the links on those sides, either board. If you can't see them from the back, just come up a little bit. But we have tinyurl.com/SIAMUNC for signing up for SIAM. This will provide you with more resources, more talk about meetings for SIAM, get to know the organization better. We also encourage you to fill out the attendance form. If you have feedback, for example, if this was a bit too advanced for your knowledge, or if you want something more different, if you literally anything at all, please let us know. Attendance at workshops will enter you into some sort of raffle that we'll have for giving away other t-shirts or other prizes. You know, maybe they could be some pretty expensive, I don't know. But yeah, thank you so much for coming out. We do have workshops every single day, Tuesday, Wednesday, Thursday, nothing Friday. And the next workshop is tomorrow. It's exploring augmented reality, virtual reality in Unity. So if you want to do something, let's say VR or AR, something like that, please come out tomorrow. It's at 6 p.m. in FBO 9. You can find out more information on our Facebook page, and we'll make sure to post information about prerequisite data or knowledge. Thank you so much.
If you have questions about the code or anything, I'll stick around for a little bit as well.